folks, welcome to another set of Chemistry 1 video notes. In today's lesson, the second lesson of Unit 5, you'll be learning about the mole. No, not the furry, cute little animal. More specifically, we'll be covering Standard C.4.4, which asks you to be able to apply the mole concept to determine the mass, moles, number of particles, or volume of a gas at standard temperature and pressure in any given sample for an element or a compound. That sounds like a lot, but I promise it's not. Let's get started. Arguably, the most important unit you'll ever learn about or use in chemistry is the mole. It's simply a unit. It has a weird name, and we make a lot of funny jokes about small rodents, but it really is just a unit. The mole helps us find how many particles of a substance we have. If we have 1 mole of something, we have 6.022 times 10 to the 23rd of that something. That number is named after Amadeo Avogadro, and it's known as Avogadro's number. You've already encountered units like this before in your life. Have you ever heard of a dozen? Well, a dozen is similar in concept to a mole. If we have a dozen of something, we have 12 of that something. A dozen donuts is just 12 donuts, right? Well, if we have a mole of something, we have an Avogadro's number of that something. A mole of donuts would just be 6.022 times 10 to the 23 donuts. That's a lot of donuts. It works in the reverse way as well. If I had 24 donuts, you'd say I have 2 dozen. If I had 12.044 times 10 to the 23 donuts, then you'd say I have 2 moles of donuts. It's sometimes called the chemist's dozen because it's just a different way to count how much we have of something. Go ahead and add this number to your toolbox of conversion factors. If you want to convert from moles to particles or vice versa, just plug it into your normal unit conversion type problems and just make sure the units cancel appropriately. Let's do some examples. How many moles of sodium atoms are there in 2.26 times 10 to the 24 atoms of sodium? Start with what you're given. Since we have atoms on top, we want atoms on bottom. According to Avogadro, there's 6.022 times 10 to the 23 atoms in 1 mole. It may not seem important right now, but when you write those down, make sure you write down what you're talking about. So you might say 6.022 times 10 to the 23 atoms of sodium on bottom and 1 mole of sodium on top. So do that math and you should get that there are 3.75 moles in 2.26 times 10 to the 24th atoms of sodium. How many molecules of methane are there in 2.25 moles of methane? Start out the same way, except this time you want moles on bottom since that's what we started with. Do that math and you get that there are 1.35 times 10 to the 24th molecules of methane. How many atoms of hydrogen would there be in that much methane? Well, since there are 4 atoms of hydrogen in each molecule of methane, we'd use that as a conversion factor. That tells us there would be 5.42 times 10 to the 24th atoms of hydrogen. The mole is really important in chemistry because we can't count each individual atom or molecule that we have and know exactly how our reaction will take place. Atoms and molecules are generally so small that it would be impossible to count up each one. Plus, it's a really big number. What we can measure easily is the mass, or grams, of a substance. If only we had a conversion factor from grams to moles. Oh wait, we do. It's called the molar mass. The molar mass of a substance is how much 1 mole, or 6.022 times 10 to the 23 particles of that substance, weighs in grams. The average atomic mass that you find on the periodic table tells you how much a single atom weighs in atomic mass units, or AMU. If you have a mole of atoms, that mass in AMU turns into the same number but in grams. So the molar mass, or how many grams there are in 1 mole of atoms, is just that atom's average atomic mass on the periodic table, with grams as its unit. Well, how do you find the molar mass for a substance? Easy peasy lemon squeezy, my friends. You simply add up the atomic masses for each atom present in your molecule. Say we have H2O. That's 2 atoms of hydrogen and 1 atom of oxygen. On our periodic table, it says that molar mass of hydrogen is 1.008 AMU and oxygen is 15.999. To find the molar mass, you'd add 1.008 plus 1.008 because you have two hydrogens, plus 15.999 for oxygen. This tells you that a molecule of water weighs 18.015 AMUs. If you had a mole of water molecules, that would weigh exactly 18.015 grams. This can and will be used as a conversion factor to convert between grams and moles of a substance. We'll use this extensively in some upcoming lessons. So how do we use molar mass to convert? Let's just stick with our water example. We just determined that 1 mole of water is equal to 18.015 grams of water. Anytime we have an equivalence like this, we can turn it into a fancy form of 1 like these, and use that as a conversion factor. So, how many grams of water are in 4.76 moles of water? Since we started with moles, we want moles on bottom. For molar mass, the moles will always be 1 because that's how many grams are in 1 mole. That's literally the definition of molar mass. Do that math and you get that there are 85.75 grams of water in 4.76 moles of water. So how many moles of water are there in 102.33 grams of water? Set it up like this and you get 5.68 moles of water. Remember, the important part of our unit conversions is to make sure our units cancel. As long as you're canceling units correctly and you're moving towards the unit you're looking for, you should be fine. Our last conversion for the day involves gases. We haven't talked about gases or the ideal gas law yet, but we will in due time. For now, you just need to know how to convert between volume of a gas and moles of gas particles at STP. STP is the standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere. STP is just an agreed upon temperature and pressure at which chemists report various properties of substances. This makes it easier for us to compare different substances because changes in the temperature or pressure can cause changes to the volume of different substances and their density and a number of other different things. Anyway, the important conversion factor that you need to know is that at STP, 1 mole of any gas that behaves ideally will have a volume of 22.4 liters. That could be 1 mole of helium, 1 mole of methane, 1 mole of any gas. As long as it's 1 mole of a gas at STP, it will have a volume of 22.4 liters. Hey, that's another equivalence. You can turn that into a fancy form of 1 as well. For example, if I wanted to see how many moles of O2 there are in 140 liters of O2 at STP, I simply set up my conversion problem as usual. Choose the correct fancy form of 1 and then solve it. At STP, 140 liters of oxygen gas should be about 6.25 moles of oxygen. Here's a little mole map that you'll get to glue into your notebook. If you're trying to go from mass to number of particles or number of particles to volume of a gas, there's no direct path. You always have to make a pit stop at moles before you go on to the next conversion. So today we learned 3 different conversions. We can convert back and forth between moles and particles using Avogadro's number. You can convert between grams and moles using molar mass. And you can convert between the volume of a gas at STP and moles of that gas using 22.4 liters per mole. Well, that's it for today, folks. As always, if you have any questions, ask.